All right, so for this first question, we want to break this thing down and, get the table of signs, get the x-intercepts, y-intercepts, all that good stuff. All right, so I'll probably take the most time on this one, and then subsequent videos I'll just do a little bit quicker. So in this case, we have this rational function. There are times where I may not give it fully factored. There are times where you may have to do a little bit of work. So in this one, I kind of do a little bit of both. All right, so first thing we'd want to do is see whether we can simplify this thing by factoring. So in the numerator, notice that we can first pull out a greatest common factor of x, which will leave us with an x times x squared minus 4. And then we can factor that into a difference of squares. We have an x plus 2, we have an x minus 2, and in the denominator, we have an x 2 and an x plus 3. Right, so the biggest mistake students make at this point is they kind of cancel like stuff too quickly. Before you do this, I would really recommend finding your domain restrictions, which are going to occur whenever the denominator is equal to 0. If you cancel too quickly, you run the risk of kind of like forgetting that there was a domain restriction. So in this case, right, so our domain restrictions occur when x minus 2 is equal to 0. So obviously that's going to be when x is equal to 2, and then also when x plus 3 is equal to 0, which is going to be when x is equal to negative 3. So then once you've done that, it's time to simplify the function, right? So our simplified function occurs whenever we cancel stuff out. So in this case now, our simplified function is going to turn into x times x plus 2 all over x plus 3. All right, so that's our most simplified version of the function. Right, so next thing we want to do is kind of classify these domain restrictions. Domain restrictions are either going to be vertical asymptotes or they're going to be poles. So remember, if this domain restriction still lives in the denominator, aka this x equals negative 3, it's going to end up being a vertical asymptote. If that domain restriction canceled completely out, like this x equals 2 did, it's going to end up being the x coordinate of a hole. Right, so we'd have 2 something for our hole here, right? So in order to figure out the y value of our hole, aka this value right there, you're just going to do f of whatever the x coordinate of the hole is, right? So it's going to be f of 2. Now notice that technically we have 2 places we can plug in x is equal to 2. We can plug into the original equation, or we can plug it into the simplified version. If you plug it into the original, right, all that's going to end up happening is you're going to get a 0 right here and a 0 right there, right? So in that situation, we can't have a 0 on the top and bottom. We get what's called an indeterminate form. So you can't plug 2 into there and get anything meaningful. So what that means is that we're going to plug this in to the most simplified version of the function. So I'm just going to plug in 2 every place I have an x. Right, so that's going to be 2 times 4, so 8 over 5. So 8 over 5 gives us 8/5, or 1.6. Right, so then we have the holes. Right, so next thing is that we want to think about some more long-term behavior, which is going to be the horizontal asymptote. So let's find the degree of the top divided by the degree of the bottom. It actually doesn't matter if you use the original function or the simplified version. You'll get the same relationship either way. So I'm going to use the simplified version. Right, so in the simplified version, I have x to the first power, x plus 2 to the first power. So that means the degree of my top is going to be 2. If I look at the denominator, I just have an x plus 3 to the first power, so it's going to be a 2 over 1. So in this case, the degree of the top is bigger than the degree of the bottom. So I'll just say degree top bigger than degree bottom. Right, so this lets us know what's going to happen with the horizontal asymptote. Whenever the top degree is bigger than the bottom degree, there's going to be no horizontal asymptote. Right, we'd have this top heavy function, so we don't have to worry about what this function does as x gets really, really large. Right, so yeah, that's all I want to say about that. So in terms of x-intercepts occur whenever the numerator is equal to 0, right? So set top equal to 0 at the top of the simplified version of the function, right? So we're going to set this x times x plus 2 equal to 0. Right, so if I do that, we're going to get, remember, everything that has an x gets a chance to be equal to 0. So that x gets a chance to be 0. This factor x plus 2 gets a chance to be equal to 0. So that means we have 2 x-intercepts. Little arrow. Right, so we'd have 0, 0 as an x-intercept, and also negative 2, 0 as an x-intercept. So we actually just found the y-intercept, right? Because if 0, 0 is the x-intercept, it's also the y-intercept, the origin. But if you were ever unsure and you want to find the y-intercept, all we do is plug in x is equal to 0 into the simplified version of the function. All right, so then now the reason that you're probably watching this video, the iffiness on table of signs. So in a table of signs, so remember, we're breaking up our domain of all real numbers with vertical asymptotes and x-intercepts. Right, so a function can change from positive to negative, like go by going through an x-intercept. A function can jump from a positive to a negative by being on different sides of a vertical asymptote. Right, so in our case, if we just look at our kind of our domain initially of all real numbers. So we had a vertical asymptote when x was equal to -3. So I was going to throw one over here. I have a -3. We also had two x-intercepts, 0, 0, and -2, 0. So I'm going to put them kind of far away because it doesn't really matter here, right? So here are our values. And just for fun, I'm going to throw a little vertical asymptote thingy right there, and those other two values will be 0 and 0. Although you definitely do not have to do this. It's just to kind of remind us what those things are. All right, so the whole idea behind the table of signs is that you want to take your simplified version of the function. So I'm going to duplicate that and bring it down. You want to take this simplified version of the function, and you want to plug in some test points that is in some interval, right? So if I look at this interval, I have values from -infinity all the way up to -3. So any x value that we choose in that interval is going to work as a good test point. It'll tell us whether the function is positive or negative, right? So I'm going to plug in just -4. So every x value we're just going to replace with -4, right? So -4, -4, -4. So -4, -4, -4. So the thing that I think sometimes students struggle a bit with is that we don't care what the number is, we care what the sign is, right? So -4 is a negative number. -4 plus 2 is going to be a negative number because -4 is bigger than, well, 4 is bigger than 2, right? So it's more negative than it's positive, or just get -2. -4 plus -3 is -1, which is also a negative number. So if we have an odd number of negatives, we're always going to get a negative value, right? Because you can think of this negative value and that negative value canceling out to become a positive. So a negative times a positive would end up being just negative, right? So we know that on this entire interval, our function is going to be a negative number. And so negative here. If I choose any value between -3 and -2, like -2.5, let's see what happens, right? We're going to get a -2.5, -2.5. Let's write -5/2, -2.5. Right, so -2.5 is obviously a negative number. -2.5 plus 2 is going to be negative as well. -2.5 plus 3 is going to be a positive number. Notice that I have two negatives. I have an even number of negatives, which is going to be a positive number always. So in this interval, our function is positive. You could also think of this as a negative times a negative is going to be a positive, right? So a positive divided by a positive gives us a positive. If I choose anything in this interval from -2 to 0, like -1, and so you would get to -1 here, -1, -1, right? So that's going to be a negative number. -1 plus 2 is going to be a positive number. -1 plus 3 is also going to be a positive number, right? So in this case, we only have one negative, just that one right there. So our function is going to be negative on this interval. Right? And if we plugged in something between 0 and infinity, in this case, we actually don't even have to do it, right? Because we've already plugged in something. We know that when x was 2, we got 8/5 as a value. So if you did use, say, 1 or 2 or anything as your test value here, is always going to end up being a positive number. Let me do that just in case. Right? So suppose we just plugged in x was equal to 1. Right? So I'm going to get 1, 1, and 1. Right? So that's going to be a positive number because 1 is positive. 1 plus 2 is positive. 1 plus 3 is positive. All positives means that we're going to be positive over here. Right? So if the goal was to sketch this function, we'd have a little bit of a different problem, but we could use this table of signs to help us out. So I don't care about sketching this problem right now, right? The goal is to be able to identify. So where's the function less than 0? Well, it's less than 0 on the interval from negative infinity to negative 3, right? So negative infinity to negative 3, and then union negative 2 to 0, right? So on that yellow and that yellow interval. Where's our function greater than 0? Well, it's greater than 0 on the other two intervals, right? So it's greater than 0 from negative 3 to, there we go, negative 3 to negative 2, and then from 0 to infinity, right? So that's going to be our positive interval, negative 3 to negative 2, and then union 0 to infinity. Notice that for being really technical, we're not positive or negative at 3, right? So we're not doing an open bracket, a closed bracket there. It's open because at the point negative 3, we're actually 0. So we're not negative or positive, we're neutral, right? Actually, technically, we have a vertical asymptote there. So at negative 2, we're not positive or negative because we're 0, right? Which is neutral value. All right, so I'll do the other ones in other videos.